Hi everyone, let's get straight into the setup for today's problem. So we have a rough inclined plane making an angle theta to the horizontal. And at the very base of that rough inclined plane, we have a chain resting on a horizontal surface. And the chain is coiled up into a pile. That's this thing here that you see on the diagram. Very important to notice that it's not initially stretched out, it is coiled up. So our chain has a linear density, in other words, a mass per unit length of lambda, and at the end of the chain is attached a ball which we're going to treat as a particle, and the ball has a mass of m. Now, as we said earlier, the plane is rough, so there's friction here, and we're going to say that the coefficient of friction between both the plane and the chain and the plane and the ball is mu. We're assuming maybe that the chain and the ball are made of the same material, so that they have the same coefficient of friction. So I've also specified a couple of initial conditions. Firstly, that x of 0 is 0. So what does that mean? Well, if you look at the diagram, you can see that I've defined x as a function of time to be the distance up the plane traveled by the ball at the end of the chain. So if we're saying x of 0 is 0, that's just putting into mathematical form this idea that the chain is initially completely coiled up. So we just have a ball sitting at the very base of the plane with a fully coiled chain. And the other initial condition that I've specified is that v of 0 is u. So you can probably guess v is the velocity of the ball, and v of 0 being u just means that we give the ball an initial impulse up the direction of the plane such that it's moving with speed u. So the question is to find the maximum distance up the plane reached by the ball, in other words, the maximum value of x of t as marked on the diagram. And the reason there is a maximum value is as soon as the ball starts moving up the plane, it's going to be being pulled down by gravity and also resisted by friction. So it's going to be slowing down until the velocity reaches 0, at which point it will start going back down the plane again. So there's some maximum distance which we're aiming to find. So we're going to do this by using Newton's second law to set up and solve an equation of motion. Don't be tempted to try and use conservation of energy here. Firstly, because there's friction involved, but even if you do take account of the work done by friction, you'll find that energy is still not conserved, because in a problem like this, there are inelastic collisions between the successive links in the chain as they're set into motion. So energy conservation doesn't really work for this problem. So Newton's second law is, of course, force equals rate of change of momentum. I'm writing it as F equals dp by dt rather than F equals ma, because the mass of the system is variable, because more and more of the chain is being set in motion over time. Right, so the mass is changing, and so we've got to use this full form of Newton's second law. First thing we need to do in order to use it is identify the forces that are acting on our system. Now, there will, of course, be some weight acting straight downwards. I'm going to start adding some force arrows to my diagrams. Let's draw downwards arrow there, label it W, and that weight is a combined weight both of the portion of the chain which has already been dragged up onto the slope and the ball itself. And so in reality, that force is going to be distributed across the entire length of the chain, because each little bit of the chain has its own weight, but we don't really care about the point at which the weight acts. We just care about its magnitude and its direction. So I'm just combining the weight of every bit of the chain and the ball into a single effective force at some arbitrary point. I've also just added a little dash line which is perpendicular to the direction of the plane, and marked in that the angle between that perpendicular and the weight is theta. That follows from geometry. You can probably spot that straight away if you've seen enough of these inclined plane problems. There is, of course, one other force which we have to mark onto our diagram, which is the normal contact force between the ball and chain and the plane, and that is going to act, well, perpendicular to the plane. I'm not drawing these arrows to scale necessarily, but let's draw a perpendicular arrow there and label that as n. And again, it's really distributed across the entire length of the chain, but that doesn't really matter. We just draw it at some arbitrary point. So now that we've identified the forces, we can actually plug them into Newton's second law and construct our equation of motion. So let's apply Newton's second law in the direction of motion, so parallel to the line of greatest slope of the plane. And we have to resolve the weight force in that direction because it has components both parallel and perpendicular to the plane. I'm going to start by writing down a minus sign because the direction of increasing x is up the plane. So gravity is tending to pull it downwards, so it needs a minus sign. So the weight is going to be the mass times g, but the mass is the mass of the entire system, which is moving up the plane, which consists of both m, the mass of the ball, but also the mass of the amount of chain, which is already on the plane. And that's going to be lambda x by definition of lambda, right? Lambda is the mass per unit length. The length is x, so we multiply them together and add those to get the total mass of chain which is on the plane. Then I multiply that mass by g to turn it into a weight, and then we have to resolve it in the parallel direction by multiplying by sine theta. There's also friction, remember, so I'm going to have to subtract off, again minus because friction is opposing the motion, I'm going to have to subtract off mu times the normal contact force using this Coulomb model of friction, where the friction is proportional to the normal contact force and the constant of proportionality is mu, and the right hand side is going to be the rate of change of momentum, so it's d by dt of something, and that something has two contributions. It's got mv from the momentum of the ball, but we also have to add the momentum of the chain, and that's going to be lambda xv again, because lambda x is the mass of chain already on the plane. It's probably also worth mentioning explicitly that the chain and ball both have to move with the same velocity v, because the chain is not extensible, so the entire thing just gets dragged up with that same velocity. That's why it's okay to put the same v in both of those momentum contributions there. So let's expand out the brackets and do the differentiation. I'm also going to switch to notation where a dot represents a time derivative, and I'm going to write my v's in terms of x just to emphasize that this is a differential equation that we want to solve for x. So your first term is going to be m dv by dt, but v is already dx by dt, so that's the second derivative of x, so I'm going to write x double dot there. Now for the second term, I'm going to have to use the product rule because x and v both vary with time. Lambda is a constant, so that's going to be a common prefactor to both bits. The first bit is going to be, well, we differentiate the x and leave the v as it is, but when you differentiate x, you get v, or equivalently x dot, and so you get lambda x dot squared. For the second term, we've still got our factor of lambda, but now we leave the x alone and differentiate the v. Differentiating v gives you x double dot, as we discussed just now, so we get a plus lambda x double dot at the end there. Now to find out what we are going to do about this normal contact force n, we can resolve perpendicular to the plane because there is no motion perpendicular to the plane, and so the forces in that direction must be balanced. The force sort of diagonally up and to the left is just n, and that has to balance with the component of the weight, which is acting sort of downwards and to the right. And so that's going to be, again, we get this m plus lambda x as the mass of the system times g to turn it into a weight. This time we project onto the perpendicular axis, which means multiply by cos theta instead of sine theta this time. So we then go back to our original equation and substitute this n into there and see what we get. There's going to be a common factor of m plus lambda x times g in both of those terms on the left hand side. I'm also going to take out a minus sign, so I'm going to write it as minus m plus lambda x g. Then you've got your sine theta from that original first term. Now you're going to have to add on a mu cos theta from that expression for the normal contact force. And for the right hand side, I'm just going to combine two of the terms together, which is the mx double dot and the lambda x double dot. We're going to factor out m plus lambda x into x double dot, and then keep our lambda x dot squared at the end. Now, because we have this m plus lambda x factor appearing in two different places, it's kind of tempting to divide by that. So let's do that and see if it makes our equation look a little bit simpler. So on the left-hand side, you're going to have minus g into sine theta plus mu cos theta. Your acceleration term is now just going to be x double dot because we divided through by that coefficient. And then you're going to have a fraction, which is lambda over m plus lambda x into x dot squared. So now we've got one of these situations where we have a nonlinear second order differential equation, which is very hard to solve directly. So we're going to use the trick of converting it into a first order linear differential equation. Essentially how that works is we take our x double dot and we write it as half d by dx of x dot squared. So we're differentiating with respect to x instead of time. You can verify this relation for yourself by using the chain rule. So just do that differentiation and use the chain rule and convince yourself that you get the acceleration. You can also look back at my last chain problem video for a full derivation of why that works. But let's use this identity for the acceleration and also multiply everything by 2 to get rid of that prefactor of a half, and then you're going to get minus 2g into sine theta plus mu cos theta let's write this as dx dot squared by dx, and then don't forget that extra factor of 2. You're going to have 2 lambda over m plus lambda x into x dot squared. So here's the differential equation we ended up with. It's the same thing we had before, but I've just flipped the sides around, and this is a first order linear differential equation for x dot squared as a function of x. And it's the type of differential equation that we can solve using an integrating factor, which is basically the method where you multiply the entire equation by a certain function that makes the left-hand side easy to integrate. I do have a video going through all the details on that if you'd like to have a look. The basic idea is you take the coefficient of the function that you're trying to solve for, which here is x dot squared, so the coefficient is this stuff here. You integrate that with respect to x, and then you exponentiate the whole thing, and then that's your integrating factor. So let's do that. I'm going to call it I of x. Usually I call it mu of x, but we already used mu for coefficient of friction. So it's going to be e to the power of the integral of 2 lambda over m plus lambda x with respect to x. Fortunately, that's pretty easy to integrate because the top is proportional to the derivative of the bottom. So it looks like a natural log. It's going to be e to the power of 2 natural log of m plus lambda x. Then you use your laws of logs to say that the exponent is log of m plus lambda x all squared, but then you exponentiate it. That undoes the natural log, and you end up with just m plus lambda x all squared. So then we multiply our original differential equation by that integrating factor, making sure to do it to all terms. So your first term is now just going to be m plus lambda x squared times dx dot squared by dx. Your second term is going to be plus 2 lambda. There is already an m plus lambda x on the denominator, so you're going to have just one factor of m plus lambda x multiplied by x dot squared. And your right-hand side is going to be, well, why don't I just copy and paste the stuff that we had originally. So you've got all of that, and then multiplied by our integrating factor m plus lambda x squared. Now, if you look closely at the left-hand side, you'll notice that 2 lambda times m plus lambda x is the derivative of m plus lambda x all squared. That follows from the chain rule. But also, dx dot squared by dx is, well, straightforwardly the derivative of x dot squared with respect to x. And that kind of sum of two terms is the kind of thing you get from the product rule. So we can write the left-hand side as the derivative of a product. More specifically, it's going to be d by dx of m plus lambda x all squared times x dot squared, right? So all of that, and then I'll just keep the entire right-hand side the same. We don't need to do anything with that for now. But the left-hand side looks much simpler, and now it's straightforward to integrate. In fact, let's do that integral. Integrating the left-hand side with respect to x just removes the derivative, right? So the new left-hand side can just be m plus lambda x all squared times x dot squared. Now for the right-hand side, you basically just have to use the power rule and the chain rule because this is basically a polynomial function of x on the right-hand side. Let's once again copy this constant prefactor, right? Theta and mu are constants for any given problem, and g, of course. So we're going to take our bracketed term, increase the power by 1, so m plus lambda x cubed. Then we divide by the new power, which is 3, but here we also have to divide by lambda, because if you were to differentiate m plus lambda x cubed, you would get an extra factor of lambda from the chain rule that we don't actually have, and so you need to divide by that to remove that extra factor. And of course we need a plus c constant of integration. So now we can make use of our initial conditions to fix the value of c. So the initial conditions, remember, were that x of 0 is 0 and v of 0 is u, where x and v are both given as functions of time. Now we can still use those initial conditions even though our equation doesn't contain time, because they're both specified at the same value of time, right? So because they both apply at t equals 0, that means, in fact, let me write this down, so that when t equals 0, that means that x is 0 when x dot is equal to u. So it's perfectly fine to just substitute x is 0 on the right hand side, well, on both sides, and x dot equals u on the left hand side. So if we do that with this equation up at the top there, the left hand side will reduce to m squared u squared, that lambda x disappears. The right hand side, you're still going to have all of this stuff, minus 2g sine theta plus mu cos theta, but the bracketed term after that is just going to be m cubed, all of that as a fraction over 3 lambda, plus c still has to be there. So then to get c, we just move the negative term over to the left hand side. I've chosen to factor out a factor of m squared over 3 lambda, which means that this m squared u squared term is going to have to acquire additional factor of 3 lambda on the top so that it cancels with this 3 lambda on the bottom. I've chosen to do that just because it makes the algebra work out a bit more conveniently later on. It's a good form to have a constant of integration in. So now we're getting closer to answering our original question, which is what's the maximum distance? And the maximum distance occurs when x dot equals 0, because that's when the ball and chain instantaneously come to rest. So they're moving up, then they instantaneously rest, and then they start coming down again. You can just plug in x dot equals 0 into that equation at the very top, and that's going to give you an equation you can solve for x, because everything else is a known parameter. We know c, we've just derived what c is. And so if we just set the left-hand side of that equation up at the top to 0, we end up with, well, let me do some copying and pasting. I can take this entire fractional term without the minus sign, right? If the left-hand side of the top equation is to be 0, then all of this stuff has to be equal to c, where c is the expression that we just derived up there. So we end up with this huge equation that barely fits on the page, and notice that they both share a denominator of 3 lambda, so we can immediately get rid of those and get rid of the fractions. That's why I chose to write c in that form earlier. Then I'm going to divide through by 2g into sine theta plus mu cos theta to get m plus lambda x cubed on its own. Now, because we're ultimately going to need to take a cube root to get rid of the cubed on the left-hand side, it's actually convenient to turn this m squared into an m cubed and adjust for that in the terms inside the big square bracket. So I'm going to turn that into an m cubed. I'm also going to split this big fraction into 2 separate terms, because something very nice happens with this second term. So your first term is going to be, we're still going to have 3 lambda u squared on the top. That was there originally. You're going to have 2g sine theta plus mu cos theta on the bottom, but with an extra factor of m on the denominator, because remember we originally had m squared. Now I'm going to write it as m cubed, just for compactness and time saving. I'm going to write that as s plus mu c for sine theta plus mu cos theta. Now what about the second term? Well, there is already an m there, so given that we have m cubed at the front now, we don't need any factors of m in our second term, and the remaining stuff is just 2g sine theta plus mu cos theta on the top. That perfectly cancels with the denominator and just gives us a plus 1 there. So after some algebra, we end up with this final result down at the bottom. I've got to that in 3 steps. Basically, firstly, I've taken a cube root, which turns this m cubed into this m, and raises all of this stuff to the power of a third. Then I have subtracted m from both sides, so we want to get rid of that m there. That's where this minus 1 comes from. That comes from subtracting the m, because I've also factored out an m in front. So that minus 1 is really a minus m. And then I've just divided through by this lambda, which is the coefficient of x. So lambda ends up on the denominator. So let's just finish by thinking about how this solution depends on theta. And theta appears in 2 places. You've got sine theta plus mu cos theta. Now, if you consider some limiting cases, firstly, when theta is very small, when theta is close to 0, in other words, the plane is close to being horizontal. Now, in that case, cos theta is going to be close to 1, and sine theta is going to be close to 0, and that means the mu cos theta term dominates there. Now, because the mu is attached only to the cos theta and not the sine theta, that means that when theta is small, the friction is going to have a more significant impact on reducing the maximum distance that the ball and chain can travel. That's quite intuitive if you think about it, because if the table or the plane is almost horizontal, then you're going to have a big normal contact force, because you've got the more of the gravity pushing perpendicular to the plane. In the opposite extreme limit, when theta goes to pi over 2, in other words, the plane becomes vertical, then sine theta is going to be roughly 1 and cos theta is going to be close to 0. In that case, the coefficient of friction in the limit doesn't actually enter the expression at all, because cos theta becomes 0. Again, that makes a lot of sense, because when the plane is vertical, the ball and chain is falling, well, rising and then falling vertically as well, and there's nothing pushing it into the plane, and therefore there's no normal contact force and no friction. So that's all consistent with our intuitive expectations. So that's it, we've solved the problem. Thank you for watching, I hope you've enjoyed, and I'll see you again soon.